Hey everybody, this is Kevin Wallace, and in this video I want to introduce you to Cisco Packet Tracer. Cisco Packet Tracer is a freely available network simulator, and it's a great fit for CCNA route switch candidates to get your hands dirty and get some experience configuring Cisco routers and switches. And for years I really underestimated Cisco Packet Tracer for a couple of reasons. Number one, I've worked with a lot of simulators over the years, but most of them were what I would call on rails. In other words, you had to go through a certain sequence of commands in a certain order. You couldn't just give a random show command or say, oh, what if I set it up this way? Would that work? You couldn't play those what if games. You had to do things in sequence. And there's certainly value in those types of simulators. I mean, after all, they can help you memorize a sequence of steps to set up a feature, but they just don't give you the feel of being on real Cisco gear. And another misconception I had was I thought you had to be in high school or college and be enrolled in a Cisco Networking Academy program. Well, as it turns out, neither of those things were true. Specifically, you can create your own topology and try whatever command you want. You can even see what real gear looks like, and you can populate modules in Cisco routers and switches and see what the LED indicators look like. And anyone can get a free copy of Cisco Packet Tracer. You just sign up for a free online Introduction to Cisco Packet Tracer course from the Cisco Networking Academy, and you then get to freely download Packet Tracer. Really, the only thing missing was a set of labs corresponding to the CCNA route switch topics, so that's what I decided to create. Now, by labs, here's what I'm talking about. I give you a .pkt file that you can open up in your own copy of Cisco Packet Tracer. And that .pkt file gives you a base topology. I've already done the basic configuration, like setting up the interconnections and assigning the IP addresses, all the basic stuff. And on screen, I give you a set of tasks. And accompanying that .pkt file is a video that sets up the lab. I explain what we're going to be doing. Then I encourage you to pause the video, do it on your own, and come back, where I give you a complete walkthrough solution. And at the time I'm recording this, I'm already well into developing that product that's going to have the topics from the CCNA route switch track. Charles Judd and I are cranking those out as we speak, but I wanted to go ahead and get you started today with this video. In fact, I'm including two videos from that series in this one video. The first video shows you how to get and install your own free copy of Cisco Packet Tracer. Then we'll jump right into another video from that series where we're going to go through an OSPF lab. You'll download a .pkt topology file. By the way, the link for that is below this video. And you'll open it up in your copy of Cisco Packet Tracer. And that video is going to discuss what you're going to be doing in the lab. And at the end of the video, I'll walk through a complete solution. So try to find about 45 minutes to an hour of time where you can go through everything in this video. And if you're already at that point, let's go ahead and jump into the first part of the video where I'm going to show you how to download for free and install your own copy of Cisco Packet Tracer. It's here from the Cisco Networking Academy site where we can download Packet Tracer. And to download it, we're going to be technically enrolling in a class. We're going to be enrolling in a Cisco Networking Academy class called Introduction to Packet Tracer. Now, we don't have to take the class. You can if you want to. It'll help you understand more about the capabilities and the features of Packet Tracer, so feel free to do that. It's not really required for what we're going to be doing, though. And you don't have to be attending a high school or a college program that actually offers the Cisco Networking Academy. This is available to anyone, and it doesn't cost anything. This is just the process we go through to get Cisco Packet Tracer. And to get to this page, you can do a web search for it, but just to make it easier for you, I created a shortcut link. You can go to kwtrain.com/pt for Packet Tracer. Let's enter our email. And it wants to know some information about me. I'll opt out of the emails. And let's create a password. We'll select my country, United States. I live in Kentucky. Gender, birth date, experience, race, military status, and I think we are ready to create our account. So let's say create account. And we can go right into the course. And when we get to the course page, you can launch the course if you want to, but I'm going to recommend that we just go to Student Resources for now. This is how we're going to get Packet Tracer. And if we scroll down on this page a bit, we'll see that there's an option to download and install the latest version of Cisco's Packet Tracer. So let's click on that. And at the time of this recording, the version that I'm installing is going to be version 7.2. It does allow you to go back and download version 7.1.1 if you want. By the way, there's also Cisco Packet Tracer Mobile. I've got this on my Apple iPad, and it's kind of cool to be able to have an iPad and create fairly complex topologies on there. And the app that I have, let's see, it's available for Apple. It's probably available for Android as well. Yep, sure is. It comes with a collection of practice examples that you can go through, so kind of cool to play with. But our focus right now, just to stay on track, our focus is we want to download the Cisco Packet Tracer 7.2 software. And we're going to do this on a Windows-based machine. Notice that there's an option for Linux or Windows 32-bit, Windows 64-bit. We're going to choose Windows 64-bit. And by the way, I say we're doing this on a Windows-based machine. Well, it's a Windows-based machine that's virtualized in my case because I'm actually running a Mac. And I'm running VMware's Fusion software to allow me to do virtualization on my Mac. And I'm running a Microsoft Windows virtual machine. And it's inside that VM that I'm going to be installing Packet Tracer, just because I have a Mac. So let's download this. And it's going to take a few seconds to download. And we'll open it up. Let's extract these files. I'll just drop them on the desktop for now. And let's run the installation. And yes, I'll allow the program to make changes to my computer. We'll read through the EULA, accept that. We can specify our destination where we want to install this. And yes, I will create a desktop shortcut. And let's do an install. I fast forwarded through the install for you so you didn't have to sit and wait for that to happen. So let's say OK and finish, and we're going to launch Cisco Packet Tracer. Now, let's explore around just a bit. We have to get logged in first. Let me do that. And here we are inside of Cisco Packet Tracer. And we've got a blank canvas before us. We can see that down toward the bottom, we've got all sorts of little icons that we could just drag and drop and start doing some pretty cool things. We've got different switches, different routers. Let's just do a super quick topology just to illustrate what's going on here. I'm going to select network devices and then routers. And we've got quite a selection of routers, including a fairly recent 4321 router. Let's select that. Let's put another one up here as well. And I can interconnect these. I can use the little lightning bolt connector for connections. And I can choose a crossover cable. And I'll go from gigabit 0/0/0 to gigabit 0/0/0. Awesome. If I want to zoom in or zoom out, we've got magnifying glass icons for that. We can scroll up and down. If I want to put some notations on the screen, I can say I want to add a note, and I can say this is router R1. And maybe I want to add another note that says this is interface gigabit 0/0/0, and its IP address is 10.1.1.1 with a 24-bit subnet mask. So I could start documenting things like that. Now, by the way, you can have the router name automatically appear and the interface label automatically appear. When I'm doing these, I typically prefer to create my own text. I don't really like where they put the router name. Sometimes it's right in line with my connection. It's hard to see. So what I will typically do under Options, Preferences, I'll go in here and say, I do not want to show device name labels. And the reason it's not showing right now is I probably turned it off previously. And I'll also check, if it is checked, that I want to always show port labels. Personal preference, I don't like to show those, or the model number. So I uncheck those, and I just create my own documentation as I'm going through it. Now let's see how we go into one of the consoles here. So let's go into R1. I'll click on it. Oh, and this is kind of cool. We can actually see physically what this kind of router looks like. We could zoom in a little bit. We can turn the router on and off virtually by just clicking this little switch. That turned it off. That turned it on. You can see the green light indicating that it's on. And this is what a Cisco 4321 looks like on the back. We can see we've got a couple of gigabit interfaces. If I want to install another interface, I can go down and say maybe I want to put a serial interface in. And I can just drag and drop that up there. Oh, I cannot do it while the power's on, but I don't really want to do it anyway. But with the power off, you could populate some of your routers with some of the available hardware here. What we want to do right now, though, is go to the command line interface, the CLI, and it looks like we're sitting at a regular Cisco router prompt. It says, do you want to enter the initial configuration dialog? I'll say, no, I do not. So I'll say no to that. And I'm at a router prompt. I'll say enable, and I'll say configure terminal. I'll give this a host name of R1. And to bring up that interface, I'll go into interface gigabit 0/0/0, and I'll give it an IP address of 10.1.1.1 with a 24-bit subnet mask. And we have to do a no shutdown to bring it up. And I can do a write or copy run star to save my running configuration to my startup configuration. Let's configure the other router. By the way, notice that the interfaces are currently down. We can see that as indicated with the little red triangles here. Let's go to R2 and we'll go to the CLI. I'll say, no, I do not want to go through the initial configuration dialog. We'll say enable, configure terminal. Let's set the host name to R2 and we'll go into interface gigabit 0/0/0 here as well. And I'll set this IP address to 10.1.1.2 with a 24-bit subnet mask. Let's do a no shutdown. And let's see, we have green triangles now. Awesome. So we do have ports that are in the upstate. I wonder if I can ping R1 from the perspective of R2. Can I ping 10.1.1.1? The first ping packet is going to time out, but the rest are successful. The reason it timed out, this happens in the real world, not just in a simulated environment like this, but when R2 was trying to get to R1's gigabit 0/0/0 interface, I gave it the IP address, but in order to properly form a frame, we need more than just the IP address. We need the layer 2 MAC address, and R2 didn't know the MAC address. So it sent out an ARP broadcast, an address resolution protocol broadcast, which basically is just shouting out to this network segment, hey, does anybody know the MAC address for 10.1.1.1? And R1 responds and says, oh yeah, that's me. Here's my MAC address. So now R2 knows the MAC address corresponding to 10.1.1.1, but that took a little bit of time, and that's the reason that we had a timeout on the first packet. No problem there. That is expected behavior. And as you could tell, we could build a fairly robust topology. We could add all sorts of devices and switches and in stations, but I just wanted to get you in here and show you how we could do a basic configuration. In upcoming videos, though, we're going to be going through a series of labs where you're going to, on your own, try to complete the tasks that I've given you, and then we'll have a video showing you the solution. In fact, let's take a look at one of those right now. Let's say we want to open, and no, I won't save what I just did. Let's say that I want to open this Ospf sample that I created earlier. Let's get that opened, and let's take a look at our topology and our tasks. It's a fairly simple 3-router topology. We're doing Ospf. We've got a couple of different areas, and we know that a router that sits in more than one area is called an ABR, an area border router. That's what we have with R2 right now. It's sitting between areas 0 and 1. And the first task says that we need to configure router R1 to have both of its interfaces, gigabit 0/0/1 and 0/0/0. They both need to participate in the Ospf routing process. Now, when we do that, we can see that those interfaces need to be participating in Ospf in area 1. When we configure R2, we're going to have one interface in area 1, one interface in area 0. When we configure router R3, both interfaces are going to be in area 0. But if you read through the tasks, the big difference is how we make those interfaces participate in the Ospf process. Notice for task number 1, it says we're going to make those interfaces participate in Ospf using 2 network commands. That's going to be in an Ospf router configuration mode. For task number 2, we're going to make one interface participate in Ospf by giving a network command, just like we did in task 1. But then we're going to go into interface configuration mode, and we'll make the other interface participate in Ospf using the IP Ospf process ID area number command. This is reminding us that there's more than one way to get an interface to participate in Ospf. We could do it in router configuration mode with a network command, or we could do it in interface configuration mode. And when we go to router R3, we're not going to do anything in interface configuration mode. We want both interfaces to participate in OSPF by giving just a single network command. And I'll give you a hint. If you're wondering, how can I make two interfaces participate with a single network command? Well, remember what the network command is doing. A lot of people get mixed up on this. The network command in router configuration mode for OSPF is not saying, I want to advertise this network. That's not what we're saying. The network command says, hey, if we have an interface on this router whose IP address falls within this address space that I've given by the network command, and that might include more than one interface, then I want that interface or those interfaces to participate in OSPF. So again, the network command is specifying an address space. And if we have one or more interfaces with IP addresses in that IP address space, we're saying that we want those interfaces to participate. We are not saying advertise this network. It might look like that sometimes, but that's really not what the network command is doing. And when we get done with this, our final task is to give some verification commands to make sure that everything is working appropriately. Can we see every network from every router? And we'll give a couple of verification commands. But for now, it's time for you to pause the video, go to the description of this video, download your packet tracer topology file that I provided you, and when you're finished, you can continue this video and I'll show you my solution. Okay, let's take a look at the solution to this lab. Task number 1 was to go to router R1 and configure both interfaces to participate in the OSPF writing process, and we were going to do that using a couple of network commands. Well, let's do that. Let's go to router R1. I'll click on it and say CLI. I'll make this a little bit larger. Let's go into global configuration mode and then into router configuration mode. For OSPF, I'll say router OSPF, and I give a locally significant process ID. In other words, this number that I just gave does not have to match on my neighboring router. It's locally significant. Now I'm going to give a couple of network statements to make my interfaces participate in OSPF. For example, let's take a look at, our top interface, gigabit 0/0/1. It belongs to the network of 192.0.2.0/24. So the way I tell OSPF that I want that interface to participate, or one way I could do it is this. I could say network 192.0.2.0, and instead of giving a 24-bit subnet mask, I give the corresponding wildcard mask. So in dotted decimal, a /24 means we've got a subnet mask of 255.255.255.0. Well, the wildcard mask is going to be 0.0.0.255. And if you're not familiar with the concept of a wildcard mask, the way you create that is just write out in dotted decimal 4 255s. On a piece of paper, you can write out 255.255.255.255, and then subtract from that the subnet mask. In my case, the subnet mask is 255.255.255.0. Well, if you do the subtraction in each octet, that gives us 0.0.0.255, and I need to say in what area I want this interface to participate. It's going to be area 1. Let's do the same thing for the bottom interface. It's in network 10.1.1.0/24. So I'll say network 10.1.1.0 with a wildcard mask of 0.0.0.255. It's also in area 1. And I'm done on router R1. Let's go to router R2. On router R2, we'll say CLI. We'll say enable, going to global configuration mode, router OSPF 1. By the way, I just said 1 because that's what I commonly use when I start out a configuration, but it's locally significant, even though it does happen to match the process ID on router R1. Doesn't have to. That was optional. And here in R2, we need to make one interface participate in OSPF using a network command. Then we need to use an interface configuration mode command for the other interface. So let's take a look at the top interface. For gigabit 0/0/0, it's going to belong to 10.1.1.0/24. Okay, just like we did on router R1, I'll say network 10.1.1.0 with a wildcard mask of 0.0.0.255. It's in area 1. And even though I could give a network command for the bottom interface, just to remind us that there's more than one way to do this, we're going to go into gigabit 0/0/1, and I'm going to tell it explicitly, hey, I want you to participate in area 0. So let's go into interface gigabit 0/0/1, and I'll say IP OSPF process ID 1, my locally significant process ID. Hey, I want you to belong to area 0, and that's how we can make an interface directly participate in OSPF. And we're done here on router R2. Oh, and by the way, notice as soon as I gave that first network command, we had an OSPF adjacency come up. So great news there. Now let's go to router R3, and here we want both interfaces to participate in OSPF. And the way we're supposed to do that is by giving a single network command. How is that possible? Well, let's see. Let's go into global configuration mode and then into router configuration mode for OSPF process ID 1, and I want to remind you what the network command is saying. The network command is not saying advertise this network. The network command is just specifying an IP address space. And any interfaces whose IP address belongs to that address space, we're saying that we want that interface or those interfaces to participate in OSPF. So what if I did this? What if I gave a network statement that encompassed all possible IP addresses? Well, if I had IP addresses assigned to my interfaces, then they would all be participating. So this would be a shortcut way of assigning all interfaces to the same area. This would not have been appropriate for router R2 because it had one interface in area 1, one interface in area 0, but here both interfaces are in area 0, so check out this shortcut. We can say network, and in order to encompass all possible IP addresses, we can say 0.0.0.0 with a wildcard mask of 255.255.255.255. Everybody belongs to area 0. And we're done on router R3. Awesome. We've now gone through and we've configured using sort of 3 different approaches OSPF on all these routers. Oh, and great news, it looks like I had an OSPF adjacency come up. That's great. Now let's give a couple of verification commands. There are 2 suggested in task number 4. You can give more if you want to. You can play with this. I encourage you to experiment with verification commands. It's going to help you out when it comes time to do troubleshooting. For starters, on router R3, let me scoot this over so we can see our topology at the same time. Move the topology over to the left a little bit. Let's say show IP route. Can I see all networks in this topology? Let's see. Yes, I can. Now, we know that we learn something via OSPF if it has the code. If it has the code of an O indicating OSPF. Now, I've got a couple like that, but they also have the code of IA after them. What's that mean? Well, that's OSPF inter-area. In other words, I learned this network, 10.1.1.0/24, which is between R1 and R2. I learned that via OSPF, but it came from a different area. It came from area 1, so it shows up with this IA tag. Same thing for 192.0.2.0/24. That's the network hanging off of router R1. It was from a different area, but I learned it via OSPF. And of course, I know about my 2 locally attached networks. So yes, router R3 knows about every single network in this topology. And I won't take time in the video to do it, but you might want to go to each router and just confirm that, yes indeed, each router can see every network. Another command that you're instructed to give in task number 4 is the show IP OSPF database command. This is going to remind us of how the link state advertisements, the different LSA types work with OSPF. Let's do a show IP OSPF database command. And let's see if it makes sense to us. Now here, because we only have 2 areas and we're not connecting to some other autonomous system, we've only got 3 different types of LSAs. We've got LSA types 1, 2, and 3. First of all, let's check out the router link states. These are our type 1 LSAs. Every router in an area generates a type 1 LSA for each network to which it's connected. So we are connected to 2 networks here on router R3, and we've generated a type 1 LSA for each of those networks. And a type 2 LSA represents a link in an area that meets a couple of qualifications. In order to send a type 2 LSA for a link, that link has to be a transit link. In other words, it's got a couple of routers on it, so it's not just going off into a switch like we have for the bottom interface on R3. And it needs to be a link on which a designated router would be elected. So in other words, it cannot be something like a serial point-to-point link, which could only have 2 routers on that link. No, here we've got gigabit Ethernet links. You bet, we're going to be electing a designated router on that link by default. So this link between R2 and R3, yeah, there's going to be a Type 2 LSA reflecting that link. And here it is. And we're also going to learn Type 3 LSAs for each network in another area that got advertised into our area. Remember, OSPF uses the Dijkstra algorithm. It works like your car's navigation system. Your car's navigation system has, let's say, a map of your area of the world, and you're trying to go from your location to another location from point A to point B. Well, your car's navigation system, or Google Maps or Apple Maps or whatever it is you use on your smart device, it's going to run the Dijkstra algorithm to say, what's the quickest way to get from here to there in terms of cost? And it will have a cost associated with all the different roadways. Interstates would have a lower cost than back roads, depending on traffic conditions. And it's going to do all this math to see what's the best path to get to our destination. OSPF is doing the same thing. Within an area, we've got a detailed map of how to get from point A to point B, and we assign a cost to each link. But what about networks that live in a different area? Well, the ABR is saying, hey, I've got all these networks that live in this area, just wanted you to know about them. If you want to go to one of those networks, send your packets to me and I'll get them there. So if I'm down in area 0, I'm sitting on R3 in this example, and I want to go to a network in area 1, well, my ABR is going to get me there. I don't need to have a detailed map of area 1. I just need to know a listing of the networks that live in area 1, and I need to know the IP address of my ABR that's going to get me there. And that's exactly what we have with Type 3 LSAs. So again, router link states, Type 1 LSAs. Net link states, Type 2 LSAs. Type 3 LSAs are summary net link states. Not summary because we're doing address summarization or anything like that. Many people get confused on that terminology. It's summary because it's summary information. I don't have a map of Area 1. I've just got a listing. That's the summary information. It's not a detailed map of interconnections. It's just a listing of networks in Area 1. And here it is. In Area 1, we've got network 10.1.1.0 and 192.0.2.0. I don't know how they're interconnected. I just know that they exist in another area. And if I want to send traffic to those networks, I need to go to my ABR of 172.16.1.1, which is router R2 in this case. Now, you could give some other commands here. We could do a show IP protocols command. That's another favorite of mine. It's going to show you things like what is your OSPF router ID, which is important when you're looking at designated routers. And here we see that we're routing for all possible networks. Our all-encompassing network statement did that. We can see the administrative distance of OSPF. We could see if we have a neighbor. I could do a show IP OSPF neighbor command. Yeah, I've got a neighbor. And it's router R2. So you might want to play around with this a little bit. Go look at the different routers that you've configured. Make sure that the OSPF database makes sense for you for each router in this topology. R2 is going to have a couple of databases. It's going to have a database for Area 1 and a database for Area 0. But we'll go ahead and officially wrap up this video, and I look forward to seeing you in our next training.